going to look today about going over problems 4 and 5. And we are going to look at question 6 as well. I'm not quite sure why I didn't assign that, but that's all right. And then we're going to move on to something called normal distributions, which we're going to look at in just a couple of minutes. Would help if my smart board was working. If you look at question number 4, Matthew went online and went ahead and tried to find the standard deviation by hand. And let me tell you, I never showed you guys how to do that. And it's kind of a pretty big calculation to do. We can look at that if you're interested in what you need to do. But I'm never going to really ask you to find it by hand in this class. This is more of a different type of a calculation that you would do in a different class. But if you go ahead and you look at the information here, okay, you're given a first block and a second block, and you're asked to find the mean and the standard. I didn't do 4. Where's 4? Uh-oh. Let me make sure I have 4. There's 4. Okay. Phew. All right, so question 4. Thank you, Ro. Did you have your homework? Okay. If you look at question 4 here, and for those of you who didn't do it, you can get partial credit here for doing it late, right? So I would suggest that you get on the ball here. So we have 10 universities in Virginia, and you're trying to find the standard deviation and the mean. And then we're going to talk about what this variance is. And quite a few of you went ahead and just realized it's just the square of the standard deviation. But let's go ahead and find it. Notice the notation for mean is that little u with the tail. It's called a mu. And the standard deviation is a sigma, and then the variance is that squared. So I need to go ahead and enter my information. How do I do that on the calculator? Where do I go? Stat edit, okay? So for those of you that were out, this is something you should be writing down in terms of your steps, right? So stat edit, and we're going to enter in our information. So George Mason is 8,684. ODU is 7,708. By the way, these were about 5 years ago. Okay, these tuitions, they've gone up since then. 10,628 for VCU. I'm sorry, that's UVA. VCU is 8,817. Virginia Tech is 9,589. William & Mary, 12,188. Christopher Newport, 9,250. UVA-Y, 7,194. James Madison, 7,860. And then Radford, 7,694. If you notice, when I'm looking at my last data value on the calculator, the parentheses with the 10 in it, what does that mean? Do you see that on the calculator? You should have that in yours as well, where it says L1 and then it says parentheses 10. What do you think that means? There's 10 values. That means, and that's a way for you to double check yourself sometimes. You should have 10 numbers in your list. We have 10 colleges or 10 universities, so I know I entered all of them. I didn't skip any. Okay, so just a way for you to double check yourself. Daniel? Are we worried about sorting our list at this point? Why would we sort? A median. We're looking for a middle value, or the quartiles if I wanted to make a box and whisker plot. But I'm not doing that here. All I'm looking for is the mean, standard deviation, and variance. So there's no need for me to sort, so I'm not going to do that. But if we go to Stat Calc, one var stats, we are looking at list 1. Your frequency should be empty, and we'll calculate. So the mean that we should have gotten is going to be $8,961.20. Since we are talking about a dollar amount, we're going to round to the nearest cent, okay? The standard deviation, which of these values on the calculator am I going to use? The one that has this symbol, correct? So I'm looking at $1,458.68. Okay, it is a dollar amount. And then if you look, the variance is another measure of spread. It does talk about how spread out the values are. The bigger the variance, the more spread out things are. And it's just simply the square of the standard deviation. So you're literally going to have to type in $1,458.68 and square it. And you're going to get 2,102,000, I'm sorry, $127,747.34. Okay? Variance is just another measure of spread. It's another value. It's simply just the square of the standard deviation. If you go further in statistics, there's reasons you have to work, mathematical reasons why you have to work with the variance as opposed to the standard deviation. But that's a little bit beyond the scope of this class, okay? So just treat it as another measure of spread. Any questions on that?
How did you get the number on the calculator?
Stat, calc, 1-bar stats. Okay? Any other questions? We're good? All right, if we go ahead and look at the next question then. We're looking at Mr. Johnson, okay? And we have two different classes. We have block 1 and block 2, and they're being allowed to retake a test, okay? So I have two different data sets, and it says to find the mean, standard deviation, and variance for both. Where do I go to enter my values again? Stat edit. And since I'm trying to do two different information, I'm going to put block 1 in list 1 and block 2 in list 2. If I want to clear out an entire list at one time, make sure it's clear and not delete. When you delete it, you end up with Daniel where you're missing some things, okay? So don't delete anything. But if you arrow up and just press clear, enter, it'll clear out the whole list at once. Clear. That's what we want to do. And then we'll put block 1 in here. Am I going to be sorting my data? Well, they're already sorted for us if I look at it. But I don't even need it sorted because I'm not worried about the median or the middle. Did you have a question, honey? That's because you deleted a list, is what I was just saying. So you have to reset your memory. Go to second plus reset all RAM. Did you find it? And then it should be there if you go back. Did it work? All right, so I've got my data. They're already sorted, not that I needed them sorted, but I want to be able to do both of these at the same time. So if you actually go to stat, calc, 2-var stats, it will do them both at the same time. Okay, and you hit enter. We're going to put X, it's going to call the list 1 or our block 1 X's. It's going to call our block 2 Y's. Is that okay? No problem. I don't really care what they call it as long as they find it. And so when we calculate it, we're going to find the mean for block 1 to be 81.2. And we're going to find the standard deviation for block 1 to be 6.8. We're going to find the mean for block 2 and the standard deviation for block 2 just by scrolling down. So just by using the down arrow key. Oops, I went too far. The mean was 72.6 and the standard deviation was 9.8. How do I find the variance? You have to square it, right? So we're just going to have to square 9.8 and square 6.8. And this is going to be an estimate because we rounded. So the variance for block 2 was 96.04. And then the rounded variance, because we did round 6.8 as well, so it's an approximation. The variance for block 1 was 46.24. Again, those are just measures of spread. When it says analyze the results, it basically is asking you to discuss which one is bigger. Which one has a bigger median, or I'm sorry, a bigger mean? Block 1 or block 2? What does that mean about block 1? We're thinking it has higher scores, but let's look at this. The full picture really requires the spread. Remember, even if it has a higher mean, we want to look at the spread. What's true about the spread in block 1? Is it bigger or smaller? So that actually solidifies our answer. Who did better, block 1 or block 2? Say it again. Well, block 1 has a higher mean and a smaller standard deviation. When the standard deviation is small, that means that most people are around the mean. They're clustered. That's a good thing. We want a small standard deviation. When we have a big standard deviation, that means they're very spread out and they're all over the place. Okay? So block 1 did better. Did I write that backwards, by the way? It doesn't make sense that block, oh yeah, it does. I'm looking backwards. Because I wrote block 2 above block 1, my mind wrote it, it's like dealing with it. But yes, block 1, this, I'll highlight it for myself, honestly. This block did better. Okay, so block 1 did better, has a higher mean and a higher, or smaller standard deviation. It means more people did well. Okay, what might be some reasons why the classes perform differently? What are some things that you put down? What might be a reason that block 1 did better or block 2 did worse? Just anything. There's lots of different reasons. Huh? More, well, actually, you can actually count the numbers. Or the same number of people retook it, right? Exactly the same number. So that's not, sometimes that happens, but not here. Give me another reason why one class performed better. One class might have just had more people that studied better or studied harder. Sure, give me another reason. Different times of the day. Sure, maybe first block is different for some. The first block is different somehow. As teachers, sometimes we see that groups of students are together because of things like ROTC or things like a vocal ensemble. Whenever you have some of these elective classes, that means that usually those people are grouped together in their other classes as well. And so that's one of the reasons you would think. All right, let's look at question 6 because I didn't assign it, and I want you to look at it and read it. And I'm going to pause the recording for a minute while I put attendance in, and I want you guys to read it and maybe come up with an answer. What do you think? You're having laser eye surgery. Do you want the standard deviation to be small, medium, or large? And tell me what you think and why. And write your answer down. What do you guys think? You want it to be small or large or medium?
Small.
Why? Why small, Patrick?
Because when the standard deviation is small, that means that the majority of the information is like clustered around a certain point, so you want it to be exact when you're doing laser eye surgery because you want it to be exact like the laser.
Okay, I agree with that. Anyone have anything to add to that? Any different way to explain why they wrote what they wrote? I love that. More precise, no room for error. It's going to be what it's going to be. I like that. All those answers are great, okay? So you definitely want a small standard deviation. You want it to be more precise. You want it to have no room for error. We call that less variability in statistics. We don't want it to be we don't want it to be very variable. We don't want one day it to be like, oh, we're really, really good. And the next day, oh, you're blind, sorry. You know what I mean? Like, that would be terrible, right? That would be just kind of awful. So we want it to be as precise as possible, okay? Any other questions on these problems? Or feel pretty comfortable with mean, standard deviation, measures of spread, measures of center? All right, so what we're going to look at now is normal distributions, okay? So if you'll go ahead and in your packet, I'm going to turn the lights up just a little bit. Do you need a highlighter, Alex? You can grab one off of the filing cabinet. We're going to highlight and write some key things that are on here as far as notes go, and then we're going to look at some specific problems, okay? So when we talk about, we're going to talk about something called a normal distribution. And back in Algebra 1, you talked about something called a Z-score. And Z-scores deal with these distributions. But I want to kind of take a step back for a minute and talk about what a normal curve is, okay? A normal distribution is a set of data, okay? And it has several characteristics that are important. It's what we call symmetrical. What do you think symmetrical means in this case? If you're looking at that particular curve that's presented to you on your paper, what does symmetrical mean? Okay, there's a line of symmetry. If you remember from geometry what that means, It has a line of symmetry, and it's the same on both sides, like Ashome said. Okay, so I'm going to draw that red line down the middle of our graph. We're on the next page, folks. Okay, and it is very symmetrical on either side, and we're going to use those ideas of symmetry to kind of answer some questions using this. So it's very symmetrical. What do you think the next term, which would be bell-shaped, would represent? What does bell-shaped mean? I don't really like that term, quite frankly, but you got to know what a bell is, I guess. Joseph, did you want to? What does a bell-shaped mean? Okay, like a bell. I've never seen a bell shaped like this. I mean, I guess I should in church when the handbells. Sure, that I've seen that maybe, but okay. Is there another word we could use to describe the shape of this than bell-shaped? There's, maybe think about, how about an upside-down U? Sort of. We talk about it flaring out on either, so Raul, look, I agree with you. In the middle it looks like that, but on either end, to the left and the right, it kind of flares out on either side. So it actually goes on forever down here and down here. And it's actually what we call an asymptote. Do you guys remember what that was back from rational functions? We can treat this as a dotted line. It actually never touches the x-axis, but goes on forever and ever and ever on either direction. It gets real close, kind of skims it, right? What about, how many modes does this graph have? 1. Isn't there only one peak in the middle? So we call that unimodal, right? So usually when I talk about normal curves, I don't like to use the word bell-shaped. I like to use the word unimodal and symmetric. To me, that means what I see here, okay? So we're going to try to write that. It's unimodal and symmetric. But it's common to call it bell-shaped, okay? Unimodal is the same thing. It just means one peak, okay? Now, the normal distribution has so it's defined by the mean and the standard deviation of a data set, okay? So for every normal distribution, if we're told that a data set is normal, so if I have a set of numbers, let's say the set of heights of 18-year-old boys, okay? Some are very, very tall. Some are very, very short, but most are in the middle. Wouldn't you agree? So that to me would maybe look like it might be normal. Some very short, so there's a few down here on the left. There's a few really tall ones on the right. Most of us are in the middle somewhere. Would you agree? And if we're thinking about heights of 18-year-old boys, what would the middle be close to? What would you think that? What height would that be? 5'10" maybe? Okay, 5'9", 5'10". Okay, okay, so it depends on. I think it's 5'9", actually, 5'9" or 5'10", but maybe not. When you're taller, boys stop growing about 22, so you can continue to grow for a while. But anyway. So why did you pick those numbers that you chose when you chose 5'8" or whatever you chose? So, thank you, Will. Say it louder. Okay. So it looks like the mean, right? The numbers that you threw out at me. So that's not a coincidence that on the normal distribution, the number in the middle is the mean. Okay? So whenever you are told and you're given a set of numbers, you're going to put the mean in the middle. Okay, whatever number it happens to be. Let's say that the number was, I don't know, we'll say that the mean in our case, we're going to say it was 5'9". Okay, we're just going to write 5'9". Okay, I'm just throwing a number out there. And let's say that the standard deviation is 2 inches. Okay? I'm telling you that the distribution is normal, and I want us to draw the normal curve that goes along with this data. for 18-year-old boys? I guess it's men if you're 18, right? I would. If anything I write, I would write down on the paper. It's why it's given to you. So if you look at what I'm giving you here, what do you see? 1 sigma, 2 sigma. What do these little sigma things represent? We know that mu means mean. What do these numbers mean? Do you remember what's that symbol? Standard deviation. So anytime you're talking about a normally distributed data set, when I go out 1, 2, and 3 standard deviations, and I can go left 1, 2, and 3 standard deviations. So let's use our 2 inches, okay? And let's go and figure out the heights in either direction. So 1 standard deviation would be 5'11". 2 standard deviations would be 6'1". And 3 standard deviations would be 6'3". So anything above 6'3" is pretty unusual. That makes sense, don't you think? Still can happen. Remember, the curve still continues on forever. But we're going to call that an unusual height. Let's go in the other direction, okay? If I'm going to subtract a standard deviation now, we're going to have 5'7". We're going to have 5'5". And we're going to have 5'3". Anything below 5'3", we're going to call highly unusual. It can happen, but it's going to be an unusual situation. Okay? So if things are normal, normal is between between -3 and +3 standard deviations above and below the mean. Okay? So you're going to be given a mean and given a standard deviation, and we can draw the curve. We can put those values all the way out. Where does the mean go again? In the middle. In the middle. Now, another key piece of information here is the percentages that you see. Very important. 68% of the data lies within 1 standard deviation away from the mean. So in other words, 68% is between here and here. 68% of 18-year-old boys are between 5'7" and 5'11". Is that okay to say? 68% are within 1 standard deviation, 1 above and 1 below. Okay? What's the next percentage that you see? Well, 2 standard deviations away from the mean is 95% of the data. So 95% of 18-year-old boys are between 5'5" and 6'1". 95% of us. If I lined up 100 18-year-old boys, 95 out of those 100 would be between those 2 heights if we knew that they were normally distributed. Now this last one's pretty important. The last one says that 3 standard deviations above and below the mean is 99.7%. So between 5'3" tall and 6'3", 99.7% is between there. Almost all. So that means that anything that's any boy that's taller than 6'3" or shorter than 5'3" would be very unusual, because 99.7% of boys are between those 2 heights. Okay? Those three percentages are important to know. Okay? Now, we're going to talk about the idea of how a z-score plays into this in a little bit, okay? But remember how you found something called a z-score back in Algebra 1? It does tie to this idea because there are an infinite number of normally distributed shapes. They're all unimodal and symmetric, but you could have some that are tall and skinny. You could have some that are shorter and fatter. You could have some that are really tall. Do you see what I'm saying? There's a whole bunch of normally distributed data. There's an infinite number of them. But if I want to compare 18-year-old boys at Stonewall Jackson High School to 18-year-old boys at Osborne Park High School, well, we'd have to standardize them. In order to be able to compare things, we standardize. And to standardize, you use something called a z-score. Okay? So it's used to standardize, to be able to compare. Makes you to be able to compare values. Okay? And we'll look at when we use that in a little bit. A z-score is used to compare. So if we're ever asked to say who did better, who is taller, whatever, anything like that, when you're comparing, you want to think z-score. And we'll look at an example for that in a minute. Okay? Well, here's an example right below it. I think you're, oh, yeah, on the back. So here's an example in context of what we're talking about. What about comparing running times of a marathon runner to somebody who runs maybe the 100 or 400, 100-yard dash or 400-meter hurdles? How do you compare those times? Would it be fair to say someone runs faster because they're only running 100 yards? How do you say who did better? A marathon runner is going to take a couple hours, right? But the 100-yard dash is going to take a couple seconds. So would you just say that the 100-yard dash always ran faster? No. You have to look at them in respect to their own groups, right? You want to compare the 100-yard dash people to the 100-yard dash people. You want to compare the 400-meter hurdle people to the 400-meter hurdle people of each, and then you're going to normally distribute each one of them, or look at them from their own normal distributions, but we're going to compare them using something called a z-score, okay? Because if we found a z-score that corresponded, let's say that Christian is our marathon runner, and let's say that Carolina is our hurdler, okay? And we're going to let Jennifer be our 100-yard dash girl, okay? And we want to say between Jennifer, Carolina, and Christian, who's better? Who's the best athlete? Well, we're not going to just figure out who ran the shortest time, because that wouldn't be fair. So what we're going to do is find a z-score to compare Christian to all of the other marathoners, to compare Carolina to all the other hurdlers, and to compare Jennifer to all the other dashers, 100-yard dashers. And the one with the highest or lowest z-score would be the best. Well, let's figure out what it means. Okay, maybe we can answer that question in a minute. So, a z-score is used to compare different things. Okay, and that's what we're going to be doing. All right. So, let's do an example. Okay? So, we have well, I'm going to go back to the other example before we jump into one. I'm going to create an example here. Let's say that Christian, so let me do 3 here. Let's say that the average hurdle time, I don't know much about track. Track stars, help me. What's a good 400 hurdle time? One second? 1 minute time. I'm like, oh my gosh, how do you even get over a hurdle? Okay, let's say an average time would be 1 minute, 30 seconds. I don't know. I'm just guessing, okay? Let's do it, and we'll say 1.3. I know that's not 1 minute, 30 seconds, but we'll say 1.3 minutes, not seconds, okay? Let's say that the standard deviation for the hurdles was 0.6 minutes. No, we're going to say 0.2 minutes. Okay. Let's say that the mean for the marathoners, I really don't know how long it takes people to run a marathon. Tell me. Yeah. 3 hours would be an average. Is that good still, 3 hours? All right, so let's say 4 hours would be the middle. All right, so we'll say 4 hours. And let's say that the standard deviation for the marathon is 20 minutes. No, let's say 30 minutes. Is it possible to run a marathon in 2 hours? I don't know anything. It is possible?
2 hours, 50 minutes.
All right, let's say 20 minutes then. All right, and then we will do the mean for our dash, for a 100-yard dash. That's usually like 7, 8 seconds, right? 10 seconds? Help me. 12 seconds for guys? Really? Okay. Is it the mean for 100 yards? Really?
It's like 14.
Oh, I'm thinking 50 yards. All right, so let's say 15 seconds is the average. Is that too slow? Too fast?
That's too slow.
Too slow for the average? Not a good time now.
It's like 14.
All right, we'll say 14 seconds. And then the standard deviation for the dash is going to be 1 second. Is it really hard to do the 100-yard dash in 11 seconds?
Well, that's like a state.
So that's an unlikely, so 1 second's okay. I'm just making numbers up, okay? So now I'm going to tell you what each of our students did, okay? Let's say that Christian, who's our marathoner, Christian, how fast did you run the marathon? Let's say you did it in 3.4 hours. I'm making it up. I don't know. Okay, you're a runner. Okay? All right, our dasher, Jennifer. Let's say that you ran the dash because you're like so fast, you're like your heels are on fire, okay? Let's say that you ran that in 11 seconds because you're going to states, okay? And then let's say our hurdler, Carolina, sorry, but like let's say you fell, okay? You hit that hurdle time, you know, those poor hurdlers, they fall on the ground, you know what I'm talking about. I'm sorry, Carolina, but you just didn't have a good performance. But let's say that Carolina fell and she actually ran it in, I don't know, 2 minutes. No, let's not say that. Yeah, 2 minutes. Let's say she's 2 minutes. I'm sorry, Carolina. You fell. You felt bad. You hurt your knee or you're bleeding. Okay? We envision this. Poor Carolina. All right? Who did better? Well, if we just look at this, it looks like Jen did the best because it's the fewer seconds. Maybe she did, maybe she didn't. But that's not, we don't want to compare times because poor Christian, he stunk it up. 3.4 out. We don't want it. That makes no sense, right? We don't compare that. So what we want to do is find the Z-score. Okay? So let's find the Z-score for the hurdlers, for Christian, the Z-score, for Carolina, the Z-score for the marathoners, for poor Christian, 3.4 measly hours. And then the Z-score for Jen, who's going to states, we think, for her dash running. So the formula is on your page, right above it, for the Z-score. It's right here. It's the value. This is like, this X value represents the Carolinas, the Jens, the Christian times. That's the actual value that we're looking at. This is, what is mu again? The mean. And what is the sigma again? The standard deviation. So in order to find a Z-score, I need all three of those numbers. Do I have all three of them for each? I do. So let's plug them into the formula and let's figure out what the Z-score is so I can compare who did better. So Carolina minus the average divided by the standard deviation will tell me what that number is. We're going to say Christian minus the average divided by the standard deviation. Well, I need to not write 20 minutes. I'm comparing hours and minutes. So do you mind if I just say, let me see real quick. Well, what is 20 minutes in terms of hours? It's a third, right? So 0.3 repeating. Mind if I just, we'll write, let's just write 0.3 just for ease of conversation here, okay? So 0.3 hours, because you want all the units to be the same. Is that okay? Because otherwise it wouldn't work. So we'll say 2, not 2, but 0.3 at the bottom down here. Okay? And then we're going to say, Jen, let's see how well she did in terms of her z-score. And let's say Jen was 11 minus 14 divided by 1. Right? Okay? So let's see who did better. Well, let's find these numbers. Okay, so 2 minus 1.3 divided by 0.2. So I have 3.5 for Carolina. Is that unusual? Well, we'll talk about what that means. The z-score 3.4 minus 4 divided by 0.3. And I get -2. So that's Christian, the marathon runner. And then I have, well, one's negative, one's positive, so definitely different, okay? And then we have Jen, good old Jen here, and she's got a z-score of -3. Okay? So what is a z-score actually measuring? Well, if I had all of these on 3 different things, okay, I'm trying to, rather than do 3 different, by using a z-score, I can put them all together on 1. I have standardized. So I'm going from 3 different normal distributions now to 1. What would the middle be? Well, if it's standardized, the middle is 0. Okay? Once I've standardized, my mean is now 0. And I'm going to go 1, 2, and 3 standard deviations above, and 1, 2, and 3 standard deviations below. Anything outside of that is unusual, okay? So I have our hurdler out here at 3.5. I have my marathoner here at -2. And I have our state champion at -3. Who performed the best? Nope. The -3 performed the best because she had the smallest time. When we're talking about track, aren't we looking for the shortest, smallest time? Sometimes you want a small z-score, sometimes you want a big z-score. It just depends on the situation and the context. But it looks like to me that Jen is our track star. Okay? No, you're looking for who performed the best, which means she's very unusual because she's down here in the -3 range. Now, poor Carolina is going to have to like hang up her track shoes, right? She's unusual because she's outside of the 3 standard deviations, but she's unusual in the other direction, right? I'm sorry, Carolina. It's just not your day, okay? That's right. It's okay. My z-score would be like a 5. It'd be all right, okay? I'd be like huffing and puffing, getting my asthma inhaler. I'd be all right, okay? We okay with why a z-score is important and what we would do to compare? All right. So what I'd like us to look at is this next first problem, okay? We're looking at a store in Fair Oaks Mall, PacSun, okay? And we're given a mean and we're given a standard deviation. What I'd like for you to do before we answer any of these questions, any of them at all, okay, I want you to draw the normal curve where the mean is in the middle and you're going to go 1, 2, and 3 standard deviations above and below. So put that 12,500 in the middle, and then go out 3 in either direction. So I'll pause the recording while we do that. So when we're drawing this, we're going to be looking for a curve that looks something along these lines. We're going to put the middle to be 1,250, and I'm just going to write it sideways so I have enough room. I'm sorry, 12,500. I'm missing a 0. And then I'm going to go 1, 2, and 3 standard deviations above, and 1, 2, and 3 standard deviations below. Because I know that 99.7% of the data is between these two values, 3 above and 3 below. So 3 above, I have 14,100, because I'm adding 1 standard deviation. I add another standard deviation, I get 15,700. And then if I add that last one, I get 17,300. Then I'm going to go in the other direction. I'm going to subtract from my middle. So 12,500 minus 1 standard deviation is 10,900. I'm going to subtract another one, and I get 9,300. And we'll subtract one more, and I get 7,700. Okay, so I've drawn my picture. That's important. So it says Monday's totals was 8,600, and Saturday's total was 16,900. Okay? Are either of those unusual values according to what I've drawn on my normal curve? They're not unusual because nothing's below 7,700, nothing's above 17,300. Okay? It says to calculate the z-score for both days. So let's find the z-score for Monday and the z-score for Saturday. So go ahead and do that for me. You have the formula. You take the value minus the mean divided by your standard deviation. So find that z-score for Monday, and then we'll find the z-score for Saturday. And tell me what z-score you get. What's the z-score for Monday? So it should be a decimal. So negative 2.4 approximately. And then we have so when we look at the other one, we're going to say 16,960 minus our mean divided by our standard deviation. And I get about 2.8, 2.78, 2.8. Oh yeah, 2.79. We'll just say 2.8. Okay? About. We're going to round to the nearest 10. Why is one of the z-scores negative and one of them positive?
Because one of them you had the sales were below average and the other one the sales were above.
That's important. That's really important. When you have the sales that are below average, the z-score will be negative. Okay? So if I'm looking here at so negative 2.4, and we have a score of, what was it, 8,600? So 8,600 is about right here, right? And doesn't that make sense that if we're doing a normal distribution that it's negative, it's to the left of the mean? And then if we're looking at the other one, we have 16,000, 2.8, gosh, that's like right here. It's almost unusual. It's pretty high, okay? So that makes sense. It says Thursday has a z-score of 0. How much did they sell on Thursday? Come on, Patrick, you're on fire today. Yeah, when your z-score is 0, you sold the mean, right? When your z-score is 0, that is the mean. Exactly. So you're going to sell 12,500. That's exactly right. Okay? Tuesday's z-score is negative 1.4. So negative 1.4. By the way, the z-score tells you how many standard deviations away from the mean you are. So if you have negative 1.4, that means you're going to have 1.4 standard deviations below the mean. So 1 standard deviation is here, 1.4 is about right here. Do you agree? So we are I'll kind of draw it with a highlighter. You are 1.4 standard deviations below the mean. That's what that z-score represents. So which one, what sold more? Monday or Tuesday? Tuesday sold more. Because we have a higher standard deviation. And not a higher z-score. I knew what you meant. Good. How are we feeling so far? Not too bad? Not too bad. All right, let's look at question 2. I'm going to let you guys read it and try it. I would look at maybe drawing the picture as well. 1, 2, and 3 standard deviations above and below, and see how well we do. How would I answer this question, do you think? There's a couple of different ways to approach it. What would you do?
You could either find the standard deviation of both, see which one's higher, or you could find the...
You mean the z-score?
The z-score.
Uh-huh.
Or you could find what they actually scored.
Either way would be okay. I could actually take the z-score of 1.6 and find Jose's actual score and work backwards that way, or I could find the z-score for Muhammad and compare it that way. Either one would be okay, does not matter. Which way did you guys prefer to do it? You found the actual score and you found the z-score. Oh. What to do from here. So the question's asking you to compare Jose and Muhammad, right? And we have Jose had a z-score of 1.6. So what Patrick decided to do is to look and say, okay, if I know his z-score is 1.6, what's his actual score? Let's figure that out, okay? So what is Jose's actual score? So if we know the z-score formula, it looks like this, right? So we don't know what his actual score is. That's this number here in the formula. I don't know what that is. We're trying to find it. But I know his z-score is 1.6. Could you tell me that if I'm looking at the numbers on the graph, about where it is? Approximately 1.6 means a little more than 1.5 standard deviations above the mean. So wouldn't you agree that Jose is somewhere in here? Because he's 1 and 0.6, 1 and a little bit more than half. So this is where Jose is. Okay, where's Muhammad? Well, he's in that bracket too, isn't he? So Muhammad's in there too. So that doesn't really help us looking at that. But so we'll continue to go on. So 1.6, we're trying to find x. The mean was 540, and the standard deviation was 1.6. No, I'm sorry, 66. How do I solve that for x? Not yet. To solve the equation I have for x, I'm going to multiply by 66. So if I multiply by 66, it cancels down here, right? So I'm going to take 1.6 multiply by 66. Helps if I type it in right. And I get 105.6 on the left. And then what am I going to do to solve for x? Nope. Add 540. So Jose's actual score was 645.6. And that's going to be an N. I know they don't usually do points, but we're there, okay? So that's Jose. What did Muhammad score? 635. Who scored better? Jose did. Now, you could have also just found a z-score for Muhammad and figured out who had the higher z-score. That would have been fine, too. What'd you say, honey? Okay, and so 1.4 is lower than 1.6, so that would have worked. Either direction there would have been okay. Good. Very good. All right, let's keep going. I'm going to do number 3 with you, and then the rest of it's going to be on, you're going to finish for homework, okay? So this is the last one that we're going to do together. What is this question asking us to do? It's asking us to figure out who brought the most pencils, who collected the most, right? So I'm looking, again, to solve for that X each time. So we're going to use the Z-score formula. The problem is that I have, what am I given in each of these cases? I'm given the mean. I'm given the, I don't care what the variance. Oh, well, kind of do. I'm given the Z-score. If I'm given the variance, can I find the standard deviation? Square root it, right? So I'm going to have to go through and square root each of these values to find the standard deviation. So let's make another column for the standard deviation. What's the square root of 25? 5. What's the square root of 16? 4. What's the square root of 36? Okay. So we're going to plug these values, and we're going to find the Z-score for period 1. I'm sorry. We're going to find the number of pencils for period 1. We're going to look for period 2. And we're going to look for period 3. And we're going to be able to solve for the number of pencils in each of those cases. So for period 1, my Z-score is 1.4. I'm looking for X. The mean was 40. And the standard deviation was 5. You're going to solve that for X. We're going to do the same type of thing for periods 2 and periods 3. Tell me what you get for each of those values for X. How many pencils did period 1 sell? So 47.5. Maybe they had a broken pencil in there. I don't know. All right, so 47.5. How many pencils did period 2? 45. Did you not get 47.5? 47. Get 47 exact? Okay, let's double check. So we have 1.4 times 5. And then we're going to add 40. Yeah, I got 47. Something happened there, Joseph. I got 47 exactly. Okay? And then this one, what'd you get? 48. Okay? So this person blocked, and that makes kind of sense, doesn't it? Because they have the higher Z-score. So we knew that they were going to sell the most anyway. But that's how many they did. I'm sorry? Okay, that's good. All right, so you guys have about 15 minutes or so to continue working. You're going to do the next 4 through 10. So it's in this packet. Just continue on. That's going to be your homework that I'm going to be looking for. Some of the problems take longer, some of them don't. But your homework is going to finish problems 4 through 10 on the normal problems in the normal. The page numbers aren't listed, but the next, problem 4 and then on the back.